Welcome to Math 31. This is a lesson on trig review, lesson 2, and we're going to look at the identities, which is a big part of in fact, probably the biggest sort of pre-calculus review for trigonometry. You've covered all these in 30 pure, and so this will be a review. I'm going to go a little further than people typically do in 30 pure, a few more identities, and draw attention to other ones that you don't cover in as much detail in 30 pure, but basically the same thing. Now you're going to want to keep your formula sheet around with you when you're doing these problems. Don't try to memorize all the identities, rather have them in front of you and get the one that you need. You will, in the course of that, memorize a lot of them, but don't pressure yourself to do so. You've always got the formula sheet available. So the trig identities, first off, identities are true equations that are true for all values of the variable. So you can have identities that are not trig identities as well, but here it'll be just trig. So they're always true, doesn't matter which variable you put in. And the batch that we're going to look at, starting off, what they call the reciprocal identities. Reciprocal identities have shown up a bit earlier. Cosecant theta is equal to 1 over sine theta. So this is always going to be true. The only exception to this is where sine theta is equal to 0, in which case cosecant of that angle is undefined. So for example, sine for theta is equal to pi rads, 180 degrees. The sine of that is 0, so cosecant is undefined at pi, so you cannot take the cosecant of pi. And then secant is equal to cos theta. This is also true that cos theta cannot be equal to 0, so that means secant is undefined for pi over 2 and 3 pi over 2. Now, occasionally people will say, I'm going to write this one up at the top, they'll say, well, okay, what about cotangent? And cotangent theta equal to 1 over tan. Now, this is true statement, except where tan theta is equal to 0. However, we don't use this one as much for cotangent and tan. Usually we use the quotient one. It's more useful. But this is still one that occasionally you may want to use, even if I don't believe it's on your formula sheet. Now, the quotient identities based on division, tan theta is equal to sine theta over cos theta. And here I'm not going to write it down for this one, but a reminder that where cos theta is equal to 0, this is the tan theta will be undefined, so that would be at pi over 2. And cotangent theta equal to cos theta over sine theta, and sine theta cannot be equal to 0. So for the values of 0 rads and pi rads, cotangent is undefined. Now, the Pythagorean identities, 3 of them, I'm not going to take the time to derive them, given on your formula sheet, and these are ones you have used probably a lot in 30 pure. Cos squared theta plus sine squared theta is equal to 1. Now these formulas can be manipulated to isolate, say, sine squared in terms of cos squared or whatever like that. And very often, in fact, that's what you will do. When we start getting to the proofs, you'll typically break them down like that. 1 plus tan squared theta is equal to secant squared theta, also on your formula sheet. And cotangent squared theta plus 1 is equal to cosecant squared theta. Now the next round of them are the sum difference identities. Now the sum difference formulas are used a little bit in 30 pure, but not a lot. They're under-tested, although they are introduced and you do get a few things on them. Here, the sum difference ones get used a lot. And they look like this. Here's the two sine ones. The sine of a plus b is equal to the sine of a times the cos of b plus sine b cos a. Okay. Sine a minus b is sine a cos b minus sine b cos a. Fine. And then the two cos ones, cos a plus b is cos a cos b minus sine a sine b. And similar thing for a minus b, except the sign changes. Now the patterns with these ones are such that people actually tend to memorize them because they can see that sine, the two sine ones are sine cos plus or minus sine cos of the other angle, whereas the cos ones are cos cos minus sine, or cos cos plus or minus sine sine. So the patterns are clear enough, but they are given to you, so you don't need to memorize them. So while we're at it, we might as well keep going into the double angle identities. Now the double angle identities are based on the sum difference identities. And if I had more time, I would derive each of these. Do that in 30 pure, but you don't have to here, because they're given to you as well. The sine, and plus you've probably already seen that. Sine of 2a is equal to 2 sine a cos a. And this is based on the idea that this is 2a is sine of a plus a. So if you use the double angle identity for sine of a plus b, where both terms were a, this is what you'd get. Cos 2a will break down into cos squared a minus sine squared a. Now the fact of the matter is using a Pythagorean identity, replacing cos squared with 1 minus sine squared, and then sine squared with 1 minus cos squared, you can get a couple different forms for it. So the cos of 2a can be written as cos squared a minus sine squared a, which is its principal form, but that's also the same as 2 cos squared theta minus 1, or 1 minus 2 sine squared theta, depending on which variable or your trig function you want to express it in terms of. All given. So this version is what you see on your formula sheet. So there are the bulk of the identities that we're going to cover, the first batch at least. And this first batch, these are ones that you have seen before. The next round you wouldn't have. So let's put them to use by proving some identities. And one of the big things that you do with identities is prove additional trig relationships, such as this. So by keeping your formula sheet in front of you or around, we can make substitutions to make the left side of this expression equal to the right side. So what the method basically is, so when we see reciprocal or quotient forms, we try to express them in terms, if possible, in terms of the primary form, that is sine and cos. And through substitution, carefully, for example, we would take secant and replace this with 1 over cos. Cotangent, well, we could replace it with 1 over tan, it's true, but cos over sine makes sense, because if you peek a little bit ahead, you'll see that a cancellation lies just in front of us. So here we divide out the sine thetas, we divide out the cos thetas, and we get 1 is therefore equal to 1. So the left side is equal to the right side, which is what we want, and it's proven. You can even use the Latin form QED, quid erat demonstratum, I believe. That which was to be proven has now been proven. Now that's an unusually simple one, but that's the method for it. So let's try some more. Cosecant theta over secant theta is equal to cotangent theta. Now one of the things you try to do with these proofs is, if possible, you do not mess with both sides. You take the dirtiest side and you break it down until it's equal to the other side, if possible. Now it's not against the law to simplify both sides of it. It's just that by doing so, occasionally you move yourself further away from the intersection point. So try to take the dirty side, make it equal to the clean side. And cosecant, that would be the left side, cosecant theta is equal to 1 over sine theta. So I'm not thinking too hard, I'm just replacing. And then secant is 1 over cos. And this is a fairly common setup where you have a complex fraction and you divide it out. You've got 1 over sine theta divided by 1 over cos theta is multiplied by cos theta over 1. And this will give you cos theta over sine theta. Now cos theta over sine theta, now when you take a look at the right side, convert it into cotangent theta is equal to cotangent theta. So we did it. QED. You don't need to put that at the end, but it is a nice touch. And of course, at the end, when you had cos over sine, there's nothing wrong with taking cos, switching the right side. So it's not against the law to switch, to work with both sides, but where possible, whatever's the more complex side, that's the one you want to simplify. Let's keep going. Number 3, tan theta plus tan cubed theta over secant squared theta is equal to tan theta. Do not cross multiply, do not intermingle side to side. what you do is apply basic algebraic principles to the left. Now, that tan cubed is a concern because even if you scan your trig identities, you'll see quickly that there is no formula for a cube function. So what we do is we algebraically factor out a tan theta. And by taking that tan theta, we get 1 plus tan squared theta all over secant squared theta. Now, the temptation to do something with the secant squared theta is probably very strong. Some of you will want to go 1 over cos squared theta. Others of you will want to use the Pythagorean identity. And generally speaking, there's no absolute wrongs with simplifying expressions using identities. You just want to make sure that you ultimately choose the most direct route. And if you don't, then you have to do a little bit more work to get it where you want to go. So if your algebra is strong and you've got good command of the identities, you may find that you don't do it necessarily the fastest way, but the job gets done. So now I take a look at this, and because there is a squared term there, I'm looking at the 1 plus tan squared theta. I'm thinking Pythagorean identities, because on the formula sheet you'll see 1 plus tan squared theta is equal to secant squared theta. So why not replace that with secant squared theta? And then things start to happen, because on the denominator we have a secant squared theta, so when we divide that out, we're left with tan theta is equal to tan theta. And we're done. We've proven that this is true for all values of theta. It doesn't matter what you put in except for the ones where it's undefined. Take a look at another one. So I'm giving examples of a variety of these ones. Not everything. You have to do enough of these so that you get totally confident on them. But and really, that's what it comes down to: is a little bit of practice. Don't. The thing you want to avoid is what they call paralysis by analysis. Don't look at these and start thinking, well, what am I going to do with this one? Start making substitutions. Follow the basic principles into the primary, and making sure that you use identities properly, and then see what happens. So this one introduces another concept we see a lot, too often actually. Sine theta plus tan theta is over 1 plus cos theta is equal to tan theta. Now, in fact, there are a couple ways to solve these ones, or to simplify these ones, but I'm going to stick to the more conservative approach, and which is, when I look at the left side, sine theta on top and 1 plus cos theta on the bottom, there's really not much you can do with them because they're already in their primary form. So I'm thinking tan theta is the only substitution I can make. So sine theta, so I take that tan theta and I write it as sine theta over cos theta, and then this is all over 1 plus cos theta. And if you're like me, when you see two fractions being added together, you're thinking, get a common denominator and multiply it out. And now, in fact, some of you will also say, well, like we were doing earlier with limits and in algebra, why not multiply the top by cos theta and the bottom by cos theta, and that's also fine. In fact, it would be quicker if you're comfortable with that step. In fact, I've just about convinced myself, why don't we do that? So instead of getting the LCD, let's multiply the top by cos theta and then the bottom by cos theta. A nice touch. And you'll see what happens is cos theta times sine theta is going to be cos theta sine theta. But when we multiply cos theta by sine over cos, the coses cancel. And that will leave us plus sine theta. And then the denominator will be cos theta multiplied by 1 plus cos theta. So what has happened with that is I've done two steps in one, and I think everybody's familiar with it from earlier. Instead of getting a common denominator on top, which would have been cos theta, and then inverting or multiplying by 1 plus cos theta, I essentially did those two steps together by multiplying by cos over cos, which is just equal to 1. Now when I factor out a sine theta on top, I'll get cos theta plus 1. And then on the bottom, I've got cos theta times 1 plus cos theta. And when we divide these out, we get sine over cos, which is equal to tan. So we did it. Now, I will in later ones, I will be more strict about getting a common denominator, because I'll use this method when it doesn't look like it's going to be a huge problem, like where everything is kind of manageable. So let us do, well, actually, I'm going to stop right there, because the next batch of questions I will record in a different lesson, because they involve different things, different methods, and I'm going to assign some questions based on these. So even though this is kind of a short lesson, it gives you the an opportunity to work on some of your identities of your own. So practice, practice, practice with these ones. Thank you for your time.